In the previous video, we worked through 3 familiar properties of Riemann integration. We will continue that in this video with properties 4, 5, and 6 here. The context again is that we have a nice integrable function f on some bounded domain. For this final one, we will need to take our domain of integration and basically split it into 2. So I've gone ahead and put that in the preamble here that we have 2 domains, A and B. They are nice domains with volume, and f is integrable on both of them and their union. So we'll need that really just for this 6th and final property in this kind of series on properties of Riemann integration. Let me go ahead and state the first one, and then we will jump right into that proof. Suppose that the function f, being a bounded function, has outputs which sit between the real numbers little m and capital M, then we have this inequality on the integral of f over a. This shouldn't surprise you, and in fact, our proof will be very fast. I will use monotonicity to prove this inequality here. You could approach it through partition. So you could take A, enclose it in a nice rectangular domain S in the usual way, and then recognize that little m and capital M are below and above the infs and sups of F over every subrectangle created by the partition. And you could approach this statement through that sense of direction, and I encourage you to do that perhaps on your own. I'm going to do what I think is a faster approach to this, given that we've already proven monotonicity. Let me first establish what the integral of a constant function over a nice domain with volume is. Let's name this new function g of x just be some constant value c for all x in A. I'm going to prove this constant function is Riemann integrable over A, given that A is a nice domain with volume. So Lebesgue's criterion for Riemann integrability will tell us that G is Riemann integrable, and in particular, I can write G. I could even think of it as the extension of G as C times the characteristic function of the domain A. And here, the domain is in Rn, so let me add little vector hats. G and F, of course, are scalar valued as they've always been in our discussion of Riemann integration. Okay, so what is the integral now of G over A? Well, if I use this breakdown of taking my constant function and thinking of it as the constant function times the constant number C times the characteristic function of the domain A, we can say that this is that constant C times the characteristic function. But we know from linearity that since this is Riemann integrable, the volume of A exists, I can pull the C in front. And now this is going to be C times the volume of A. And that's exactly the expressions that we will use in just a moment in order to situate the integral of f between these two bounds. The rest of the proof is very fast, as you're probably imagining. We are going to treat little m and capital M as constant functions. So by monotonicity, which we have already shown for the Riemann integral, since the constant function little m is less than or equal to f of x is less than or equal to capital M on A, their Riemann integrals have the same sense of inequality here. So we can say the Riemann integral over over A of little m is less than or equal to this, less than or equal to this. And by the computation that we just did, we know what the left and right-hand sides are. Little m times the volume of A is less than or equal to the integral of f over A is less than or equal to capital M times the volume of A. So pretty straightforward. We are done with this statement, but actually we will cite this result in just a moment for property number 5. We are going to use property 4 to prove property 5 here. And then when we are done with this proof in words, I will put up a visualization for both of those statements. So there's a really nice way to see what both properties 4 and 5 communicate geometrically to us about the Riemann integral just for a function of one variable. Before I write this proof down, though, I'd like for you to take a moment to try this on your own. So really challenge yourself to see if you understand how to take what we just did and apply it to this context. Let's go ahead and pause for a moment, and then I will return and give you a couple of hints if you need a push. So here is a hint, or rather a pair of hints. And these come from the hypotheses of this statement. If you reread the preamble at the top, we have a lot more going on than we did in the previous statement. In particular, f is not just a bounded Riemann integrable function, it is actually continuous, which is a strong hypothesis in the context of Riemann integration. So f is continuous, and then a is compact and connected. What properties have we covered for continuous functions on those kinds of sets? So let's focus on compactness first. F is a scalar valued function which is continuous on a compact set. You should be able to write down about 3 statements about F. One of them is very applicable here and also connects back to the statement that we just proved. And then once you kind of explore those ideas, I think that's when you want to bring in connectivity. So since A is connected and F is continuous on a connected set, what all can we say about the image of F on A? And in particular, there was a very famous theorem there. Keeping with the theme of this exercise, I'm back just to do a couple statements and then we'll pause again because I really want you to try to get to the ending before I do. So since F is continuous on a compact set, F is uniformly continuous. That's not really relevant here, but it's a nice thing to remember. The image of F is compact. And in particular, the more specific statement that you can make here is the extreme value theorem holds for F. So we know F is bounded because it's continuous on a compact set, but it doesn't just have an infimum and supremum, it has a minimum and a maximum. So let's lift that up first. Since F is continuous on a compact set, by the extreme value theorem, which I would call EVT, there exists a minimum value for the set of outputs that F takes on A, and it's a minimum, so it's attained. It's not just an infimum, it's actually attained. Okay, so let's say there exist little m and capital M, these are real numbers, so that little m is the minimum of all of the values that F takes on A, and capital M is the maximum. Okay. As I said a moment ago, I'm going to pause, and if you got this far, great. If you didn't, now you know what the first step I think should be, and see what you can make of it from here. Hopefully, little m and capital M here reminded you of the exercise that we just did. So by number 4, we can say immediately that little m times the volume of A is less than or equal to the integral over A of F, and that is less than or equal to capital M times the volume of A. This is just a restatement of number 4. What's special here is that little m and capital M are not random lower and upper bounds. They are, in fact, minimum and maximum. So they're slightly more specific than they were in the previous statement, but they fit into the family of values of little m and capital M. All right, what I would like to do now essentially is divide this pair of inequalities, this triple inequality, by the volume of A, but actually I need to be careful there that I'm not dividing by 0. So let's do 2 cases where the first case is the interesting case and the second case is kind of the trivial one that maybe we should have peeled off at the very start. But let's assume for a moment that the volume of A is positive. Perhaps we're integrating over a nice rectangle or something like that. If the volume of A is greater than 0, we can divide this by that volume and we get little m is less than or equal to 1 over the volume of A times the integral of f over A. I'll just write f dv, and that is less than or equal to capital M. I'm going to pause here again, see what you make of this, and here we need to bring in the connectedness of A. The fact that f was continuous on a compact set gave us the EVT, the extreme value theorem. Now we're going to use that f is continuous on a connected set with a different but similarly named theorem. That's the intermediate value theorem. And I think it's a little harder to see it immediately when you look at this inequality, but remember, this is a function output. This is another function output. So the minimum and maximum values for f here are attained. And then this is a number between two values attained by f. So what the intermediate value theorem tells us is that for every value between one function output and another in a connected domain, there's a place where the intermediary value is attained. So that's the application of the intermediate value theorem here. By the IVT, in the interest of space, I'm not going to write it, but this is applicable because f is continuous on a connected domain. So by the intermediate value theorem, there exists a point P in this domain such that P attains this value that's sitting between two function outputs. And then this is the conclusion, just phrased a little bit differently. So let me just kind of write arrow over. If I bring this to the left-hand side now, we can say the volume of A times f of p here, turn that into an f of p equals the integral over A of f dv. This was, I think, the more interesting case where A had a positive volume. We just need to say maybe one sentence to clean this up for the case where A actually has 0 volume. See if you can get to that pretty quickly. I will write it down in just a moment, and then we will look at a visualization of both statements 4 and 5. Please do write this down in your notes just to have it for total completeness for this proof, but I'm just going to say the proof where the volume of A equals 0 out loud. If the volume of A equaled 0, then, this side is 0, this side of 0, so of course this middle term is also 0. You can get to that directly. So we have that the integral of f over A is 0. That's the left-hand side of our desired inequality. And then it turns out for every single p in the entire domain, we would have f of p times 0. So 0 equals 0 is what this becomes in the situation where the volume of A is 0. Okay, so again, the more interesting case is this one, where we get to apply the intermediate value theorem in a nice creative way. Let me step aside, then I will erase this, and we will just talk about how to think geometrically about these two first statements. I want to make sure that you have a very good sense of the geometry of statements 4 and 5. They relate to ideas from integration for, say, functions of one variable, which I think you know very well. So let's just make sure to shine a light on that. Property 4 told us that if we have some lower bound m and an upper bound capital M, then m times the volume of A was less than or equal to the integral over A of f was less than or equal to capital M times the volume of A. I'm going to put up here a picture of a continuous function f over an interval from little a to little b. So that's just some closed bounded interval on the real number line. It doesn't have to be continuous for this statement, but we'll use the same picture for statement 5 where it was necessary that f was continuous. In this situation, the volume of A is just b minus a. So we have little m times b minus a is less than or equal to, here I'll write specifically the integral from a to b of f of x dx is less than or equal to capital M times b minus a. Now geometrically, we think of this as a width. And your function values are like heights. So if we have bounds on those function heights, you want to think of those as heights as well. They're heights along the y-axis. So this is a height. And same thing here, we have a height, capital M, times a width. Sorry, squeeze this in here. So both of these products are a height times a width. So they are rectangular areas. On the left, so we have like a small rectangular area and a large rectangular area. And then what are we computing here? When we do the integral of a function of one variable from a to b, we are computing the area enclosed between the x-axis and the graph of f. So in this picture, what I would like to do is, first let's just do the middle part. So here is what we think of as the integral from a to b of f of x dx. So it's this area under the curve. Now I could pick any value little m that sits below the graph of this function, that's a suitable lower bound. And likewise, any value capital M that sits above the graph of this function. And we're saying that the true area under F is some area measurement between this rectangular area and this one. So it's a very geometric idea. Now, when we talk about property 5, the mean value theorem for integrals, why is it called even the mean value theorem? Well, mean is like average. So there's some notion here of an average value for this function f over this domain. Now, what that says is if I imagine instead of this kind of random lower bound and random upper bound, let's move them to be the actual minimum and maximum values for this function so that this rectangular area sits just underneath the graph of f, and this rectangular area has a top bar, which is just over the graph of f. So we've got like the tightest rectangles that enclose this area for f. What the mean value theorem for integrals told us is that there is some number p, which I computed exactly to be there, so that f of p times b minus a in this context is equal to this area. So again, this is a height times a width. It's kind of like if we imagine that this area does like this one, it kind of goes up and down. It's not a rectangular area. There'd be some way to sort of bulldoze the area into a rectangle whose dimensions were the width of the domain from B to A together with this height, which we recognize as a function output. So it's like we could smooth out this lumpy area into a rectangular one where this rectangle that I computed it numerically to be exactly correct, this new rectangular presentation of the area under the graph of f, we want to think of that as like sort of some even measurement because it, we came up, we came down. It's somehow representing the average output for f over this interval. So we say that, like where do I squeeze this in here? The average value for f, this is a formula you typically learn in calculus, is 1 over b minus a times the integral from a to b of f of x dx, like that. This we're now recognizing as the value of f of p. So this average value is attained by the function. This is a mean value statement. So there's a point where this average notion, this average function measurement is attained by the function. Okay, so both statements 4 and 5 relate the idea of this kind of area or general volume computation when we do Riemann integration to what here works out to be nice rectangular areas for, say, a function of 2 variables over some blob shape, like this picture I've tried to sketch here. We could think of the analogous notions of m times the volume of A and capital M times the volume of A as prisms. So a prism that has the same base, but some height, which is fixed at these numbers. So these would always represent heights. It's just that this is going to be your base measurement. Okay, I hope that helped motivate these two properties. So they're not just random properties. They give us a sense of what we're computing and how we can better understand it when we do a Riemann integral. We have one more thing to prove in this video. While I've put this property as property number 6, so that it's last in this video, this actually follows the exercises that we did in the previous video more closely. So this is unrelated to this mean value theorem geometric interpretation that we were just looking at, kind of a standalone statement here. Again, I don't have the preamble here from the first slide, but basically imagine that we have 2 domains, A and B, and both of them individually have volume. So let's say that's part of A, and this is part of A, and it's also part of B. Okay, so here's my great picture. This is A, and this is B. And f is Riemann integrable over each of these 2 domains individually, as well as their union. So that's part of the hypothesis. We have a Riemann integrable function on A and on B and on this union. What we are also going to assume, as I tried to sketch here, is that A intersect B has measure 0. So I just kind of put them in a line here, but I'll give you the more common way to see this in just a moment. If that's the case, then if you want to compute the integral of f over A union B, what you can do is just integrate f on A integrate f on b, and then add those two separate measurements together. So the fact that their overlap has measure 0 means that when you do this additive operation here, you're not going to pick up anything extra. The common way to see this, so if you want like the most common application of this statement, is when we have a function and we integrate from, say, 0 to 10 f of x dx, and perhaps for whatever reason it's more advantageous to do this at 0 to 4 f of x dx plus 4 to 10. So here, the domain A is from 0 to 4. That's a closed bounded interval. B is 4 to 10. They do overlap, but in a single point which has measure 0. So this idea of taking a domain and splitting it safely into two that you can just add together is like this statement. The proof is actually pretty fast because there's a clever trick here. So I will show you the trick. It's pretty neat in my opinion. So perhaps both in the last video and in this one, I'm ending with what I think is the cleverest proof. What we're going to do in this proof is take f and think about what restricting it to the different domains here would look like. So in particular, start to write this down. Notice if I take f and restrict it to a, what I mean by that is that whenever I plug a point from a into f, it's just going to be f of x. But whenever I plug something outside of a into f, it's going to be 0. We can think of the restriction of f to a as f of x times the characteristic function of a. And that's the function that I would work with in order to do the Riemann integral of f on a. Likewise, if I take f and restrict it to b, that's f of x times the characteristic function of b. And that's the construction that gives us the Riemann integral of f on b. And we also know that f is Riemann integrable on the union of a and b, which of course we can decompose into f of x times the characteristic function of a union b. Now let's consider the domain where we don't yet know that f is Riemann integrable. So if I want to ascertain if f is Riemann integrable on a intersect b, what I would do is think about the product of f of x with the characteristic function of this intersection, a intersect b. I don't immediately yet know how to work with this directly, but what we're going to do is take this product and rewrite it in terms of these expressions where we know that integrability holds. And then we'll use linearity as a little preview. But before we get to that, what I would like you to do is just an exercise. Take this idea that f is itself whenever x is in both a and b, otherwise it's 0. And see if you can rewrite this product using these three expressions. It's kind of like an inclusion-exclusion principle, so just take a moment to try to do that. If you've seen the principle of inclusion-exclusion before, you probably knew immediately what to do. If not, let me just put down the formula and then I'll show you like a justification of why it works. I'm going to omit the dependence on x just to squeeze it all on the board efficiently. So this can be rewritten as f times the characteristic function of a plus f times the characteristic function of b minus f times the characteristic function of their union. Okay. If you haven't seen this before, let me just give you a quick sketch of why it works. I think a Venn diagram will work here. So let's imagine this is the set A. Now for the theorem we're trying to prove, A and B overlap in a measure 0 set, but for this formula, we can imagine kind of a sizable overlap. Doesn't matter. We want this product to be 1 in here and 0 everywhere else. So let's check that's what we get here. Well, if we are completely outside of A, B, and the union, of course, if we're out here, then we get 0 plus 0 minus 0. No worries there. That checks out. If we're over here on the left side of this graphic, because we are in A but not in B, then we would get 1 plus 0. And then since we're in A, we are in the union of A and anything. So minus 1, overall that's 0, which is what we want it to be. And likewise over here, we get 0 plus 1 minus 1. Okay, so outside of the intersection, we are indeed 0 as desired. In the intersection, we're going to get 1 plus 1 minus 1. leaving us with just 1. Okay, so this decomposition is correct. And now that we have written this expression as a linear combination of Riemann integrable functions, it is also Riemann integrable. So linearity tells us that f is Riemann integrable on A intersect B. But by hypothesis, this set has measure 0. And we now conclude that on this intersection, the integral of f is 0, because I'm running out of room, so I'm going to erase this in just a moment, but this has measure 0. All right, so f is integrable on A, it's integrable on B, it's integrable on their union. That was all by hypothesis. Now we know that the intersection doesn't introduce any bad behavior, so we have that f is nicely behaved on this measure 0 set, which is the intersection of A and B. We now want to say that we can take f on the union of A and B and split it up into the integral on A plus the integral on B. To do that, we are actually going to take this linear combination and rearrange it to solve for this expression that gives us a way of evaluating f on this union. So I'm going to step away in just a moment and erase everything. I will rewrite this formula where I've solved for this product instead of this one. So just moving things over like that. And that will allow us to go immediately to the desired conclusion. Here's where we left off, just rearranging some terms so that what we've done is solve for the product of f and the characteristic function of A union B as this linear combination of f times the characteristic function of A, f with the characteristic function of B, and then f with the characteristic function of A intersect B. Now we're just going to integrate. Since we've got different domains here, I want to be very clear about why this integration works, and that's because ultimately all of these integrals are defined as happening really on a domain, which is a nice rectangular domain enclosing each of the domains. So let me pass back to that just because we have different kind of domains of integration. So let S enclosing A union B to give us a rectangle that works for all of the domains be a nice rectangle in the usual way. Then what I'm going to do is first integrate over S and then pass down to the integrals that we actually want. So we can say the integral over S of this product oh gosh, I'm going to run out of room. I'm going to omit the of x in the remaining expressions, otherwise I won't be able to fit it. So let me say over S of f times 1a dv plus integral over S of f times 1b dv minus, we're here, I'm using linearity. Let me add that note in just a moment. The integral over S of f times the characteristic function of A intersect B, dv. Okay. What's happened here? We've used linearity. Like that. This is, again, setting up an integral which is consistent with respect to the domain of integration, but really integrating over S, each of these products is how we define the integrals of, say, f restricted to the union, f restricted to A, f restricted to B, and f restricted to the intersection. So now we can pass down to the different domains of integration here, i.e. the integral of the integral of f over A union B is equal to the integral over A of f plus the integral over B of f. I'm almost there, but this marker is running out. Minus the integral over A intersect B of f. But actually, we know that this is 0. So let me just drop down one more line. And we are done. Okay, so this was 0, as we said a moment ago, because this domain of integration here has measure 0, and we proved that integrating over a measure 0 set produces an integral which is 0. All right, We're done. So we looked at 6 properties of integration across 2 videos. We're going to keep talking about Riemann integrals, but we'll bring in some new notions over the next few videos. Thank you for your attention.